announcement to make. All the sessions from Club D, a very small room, will be moved to this room after this plenary session, so there will be a lot more space. Then it is my pleasure today to introduce Edouard Barth. Edouard Barth is currently a professor at Collège de France in Aix-en-Provence in France. It's one of the most prestigious positions you can ever get in France. He's also been, last year, nominated a member of the Academy of Science in France. And he has received many numerous awards, and I won't give the list here. Edouard has become one of the most prominent scientists in the field of paleoclimate and paleoceanography, and he's been focusing on glacial and interglacial changes, trying to understand these transitions. And he's been using geochemistry, all sorts of geochemical archives and geochronology. And he's going to be telling us today about the geochemical records and sediments and how they can tell us about something about the last deglaciation. I've known Edouard for about 27 years in very different circumstances, because last time when we first met, we were playing in the same basketball team. So today it's my pleasure to introduce Edouard Barth.
Thank you, Bernard, for these very kind words. And we went, in fact, to the same school in Nancy way back in the past, more than 20 years ago. So it was a pleasure, and it's still a pleasure, in fact, to interact with Bernard. So I would like first to thank, in fact, the organizers for inviting me. And this will give me, in fact, the opportunity to show you and to illustrate what we are doing on that topic of the last deglaciation, and more recently on its impact on rivers, the work that we are performing at the Serrège in Aix-en-Provence. And I would like first, in fact, to cite a few of my colleagues and collaborators in Aix-en-Provence. So this is a teamwork, and there are students and long-time colleagues at the Serrège. And we have also some direct support from different agencies like the Commer Foundation, IODP, the ESF, and the European Community. In order to set the scene, I would like to show you, in fact, the state of the planet during the glacial maximum. I mean, we have seen this picture probably hundreds of times, but it's good, in fact, to see it again. This is an old map. This is the climate, the original climate map that is now 30 years old, but it's still good for the big picture and to see what we want to see in the northern hemisphere. We can see that Canada was occupied by a very large ice sheet, the Laurentide ice sheet. We had also an ice sheet in northern Europe, the Fennoscandian ice sheet. And of course, the climate at that time was very harsh and different from today, much colder, much drier. And we had a massive drop of sea level of more than 100 meters. I will come back to that in a few minutes. And of course, even if it is not shown on that picture of the northern hemisphere based on the climate map, the drainage basins on land were completely changed. I mean, one of the, for example, the observation that you can readily see on that map is, for example, that the Bering Strait was above sea level at that time. And it was, for example, possible to walk between England and France at that time. And these are things that are major changes of the topography in relation to the coastlines and the rivers. Let me give you, in fact, a few words about what we are doing on the front of studying the last deglaciation. We do that very accurately with corals by drilling corals either onshore or offshore islands, tropical islands. So that's the good part of this kind of work. I started, in fact, to work on that in the late 80s when I was collaborating with Rick Fairbanks at Lamont. And since then, since being back in France, we have been concentrating with the group at Serrège on islands in France, in French Polynesia, especially in Tahiti. This is a picture of the harbor of Tahiti that shows, in fact, where we obtain vertical and deviated drills towards the shore. This is a picture of the reef under the water of Tahiti. And obviously, in order to complement, I mean, we have been working with those onshore cores for many years, since the late 90s. And we wanted, in fact, the complement story equivalent to what we had done at Barbados by drilling offshore. And it took us many, many years, in fact, to convince IODP, in fact, to drill offshore the barrier reef of Tahiti. And actually, the proposal was submitted in '98, but it's only in 2005 that the expedition came to light as Expedition IODP 310, and we are still busy studying, dating, and interpreting the last data today, in fact, in the lab. So what I would like to show you is the state of the status of the sea level curve that we reconstructed for Tahiti based on the published information and the still unpublished information. This is an updated graph showing, in fact, the heart of the last deglaciation between 9,000 years before present and 19K. Everything is expressed here in calendar age in kilo year before present, based on uranium-thorium dating of the different corals. And what you can see here is that each coral is represented by 1 point. So here is the scale of the sea level. I mean, here the scale is very large. It's more than 100 meters. And the gray symbols represent, in fact, data that were already published and are based on onshore drills. And what we added with the Tahiti IODP cores is represented in colors. So I have no time, in fact, to explain to you all the details, because it's important also to not only to date corals, but also to identify them to see if that precise coral is living at close to sea level or if it is a deep living corals. For example, when you drill offshore, it's clear that the uppermost part of the corals is always made of deep living corals. So this is the reason why I contoured, in fact, these as deep living corals. But basically, the main answer is that the sea level rise can be seen with this red curve, which is the upper envelope of the curve. I mean, we do that more precisely by identifying the species, but at the same time, we can identify directly on that graph a massive and large change of sea level by more than 100 meters over a short period of time of something like 5,000 to 10,000 years. And the last deglaciation is characterized by mainly one short meltwater pulse 1A. So that's a work that is still ongoing. This compilation based on the onshore and offshore drill core is still being in review. So it's a paper that is written by Pierre Deschamps and colleagues, and we are still busy, in fact, trying to interpret the data. So this is basically, I don't want, again, to look at too much of the details, but this is more or less compatible to what we had reconstructed for Barbados. This is a compilation of the data that were obtained either on good coral representing sea level Acropora palmata or deeper living species like this one, on corals that were collected offshore Barbados. So this is something that we contributed in the late 80s and early 90s in collaboration with Rick Fairbanks. And since then, Rick Fairbanks added a few points. And basically, the main answer is that there is a meltwater pulse 1A that is compatible if you take into account the bathymetry of the corals and the timing with what we see at Tahiti. So basically, the picture is a massive change of sea level by more than 120 meters over the course of that time period, 9 to 19K, with a massive meltwater pulse at about 14.5. So this, of course, this sea level rise had a massive impact on climate. Direct impacts. For example, at the beginning I was showing the fact that the Bering Strait was above sea level. It was possible to go by foot from Siberia to Alaska. And by modeling, and it's also possible to use paleoclimatology to show that, it's possible, in fact, by modeling to show the effect, in fact, of the closure or the opening of the Bering Strait, which is directly linked to the sea level rise. So this is from a recent work that was published in 2010 based on modeling at NCAR with the Ocean Atmosphere General Circulation Model, OAGCM, the effect on the global climate of the closure or the opening that would be the opposite map of the Bering Strait. In fact, today there is a lot of exchange of Pacific, low salinity Pacific water between the North Pacific and the Arctic Ocean, and there is also exchanges between the Arctic Ocean and the North Atlantic, and because of this, and because this is affecting convection zones, it has a strong impact on the heat transport in the ocean, and when you do the calculation, it also affects the atmosphere. So this is a map showing, in fact, the direct impact, the geometric impact of closing or opening the Bering Strait. There is another effect of the sea level rise, which is linked to the fact that the rise is due to melting of ice sheets. And of course, the ice sheets are made of water. Fresh water is invading, in fact, the ocean, especially the North Atlantic, because of the location of the ice sheet. And it's known both by modeling and also by direct information in the deep sea sediment that it had a dramatic effect on the climate. These are maps, in fact, that are just there for the sake of illustration. These are maps showing, in fact, the effect of a massive meltwater injection that is linked, in fact, to melting the ice sheet in the North Atlantic and on climate. In fact, what we observe by modeling with ocean atmosphere general circulation model is a massive cooling that is not directly due, in fact, to the meltwater, but it is due to its effect on the convection zone, on the hydrology, on the density of surface water, and then, in turn, on the heat transport by the ocean. So it has a clear effect both, and you can see that both with fully coupled AOGCM and also with simplified models. So this is a compilation of many model runs. It's not one single result obtained with one particular model. This is a comparison based on many models that have been run with the same experiment, trying to compare the same experiment. There is also an importance of the deglaciation because we expect, in fact, a pulse of chemical and erosion flux to the ocean. Chemical weathering is changing through time. It's not possible, in fact, to study elements such as strontium, magnesium, and so forth by assuming that there is a steady state between input and output. So I took these graphs, in fact, from a recent paper by Vance et al. That was emphasizing, in fact, we were emphasizing, in fact, the effect of the deglaciations on the budget of elements, and they were concentrating their paper on strontium isotope, but this is valid also for all sorts of elements. So they were basically recapitulating, in fact, the fact that people were expecting large chemical weathering fluxes during deglaciation. This is the penultimate termination. This is the last deglaciation, which is highlighted in green, which is the one that we are dealing with today. And these are graphs that are showing, in fact, the variability of the weathering rate on Canada. There are different works that are summarized on that graph. You have also large input of sediments in the Ganges, Brahmaputra area, and also rivers from the Alps. And what the demonstration by Vance et al. Was that it's, in order to understand, in fact, for example, the strontium isotopes in the ocean over a long time scale, it's crucial to take into account deglaciation and the variability of the flux of those elements to the ocean. So we have to study the deglaciation. In a way, what we need is to take also into account the spatial variability, which is existing. So this is taken from a recent paper, a recent book, in fact, that was just published by John Milliman and Farnsworth. This is a map showing, in fact, the modern estimate of suspended sediment input by the rivers. And what we can see, for example, that there is a domination by the rivers that are affected by the monsoon, the Asian monsoon. But what we would like to have, in fact, in order to plug that into models and to really fully understand the biogeochemical cycles of elements and also its feedback on PCO2 that I mentioned on one of the slides, we would like to have this type of map also for the LGM, for the last glacial maximum, but also for the full transition. And this is a long-term goal that we should aim at. One way, in fact, to look at changes of the river output is to drill and to study marine sediment cores that are collected directly in front of modern and past rivers. So these are just pictures of the research vessel that we use in France. Each time that you see MD, this is a core that was collected by the Marin Dufresne, and the international community knows that. It's not only the French who are using MD cores. And this type of work is not new. In fact, it has been, many people have been trying, in fact, to look at the output from rivers, and one particular problem that was studied way back in the past was the outlets that drained, in fact, the waters that were coming out from the decaying Laurentide ice sheet. So this is a graph, a map that is showing, in fact, the decaying Laurentide ice sheet midway during the last deglaciation. You can see that it has shrunk. It is smaller than the picture that I showed at the beginning. There is also a progressive lake, the Lake Agassiz. And over the course of the last glaciation, potentially several outlets could have functioned. In fact, the Mississippi, through the Mississippi River, the St. Lawrence, the Hudson, and also the Mackenzie directly into the Arctic Ocean. And this is a long-time problem that people have been trying to tackle. And there are, even since the 70s, for example, there are papers by Cesare Emiliani or Kenneth and Shackleton. More recently, Wally Breuker, in fact, wrote that paper showing beautifully that the dilution by fresh water over the course of the last deglaciation. Here you have the ages that are represented in years. In fact, here you have 14,000 years. So it's in the middle, in the early part of the last deglaciation, 14.6, and so forth. So this is the core depths. And by using oxygen isotopes measured in foraminifera, it was possible, in fact, for them to identify the dilution effect by the fresh water coming out from the Mississippi due to the melting of the Laurentide ice sheet, the decaying Laurentide ice sheet. And one of the problems is that at that time, there was a drop of this drainage dilution during the Younger Dryas cold event. And at that time, Wally Breuker proposed that very probably this time corresponded, in fact, to a rediversion of the flow towards the east through the St. Lawrence River. And this has been a controversy since that time, in fact, basically. The drainage during the Younger Dryas still remains mysterious. At the beginning, people thought that they identified it through the St. Lawrence, but then many other researchers, especially Anne de Vernal, Claude Hilaire-Marcel, demonstrated, in fact, that it was not the case. And very probably it's the drainage during the Younger Dryas came, in fact, through the Mackenzie River directly to the Arctic Ocean. But there is still ongoing work on that subject. That is very important to understand how the melting proceeded and also where the meltwater went, because it is important also to see if it had an impact on the global ocean circulation. The same type of complexity happened also for the Fennoscandian ice sheet. This is just a picture, a graphic, very simple, showing in fact that the equivalent event that happened with the drainage of the Agassiz Lake happened also with the Fennoscandian ice sheet that was during midway of the deglaciation had a massive progressive lake, the Baltic Lake, that suddenly drained, in fact, into the North Sea at about 11,000 years before present. So this type of work is also applicable to the other ice sheet. In order to contribute, in fact, to that problem, we studied in Aix-en-Provence a core that was collected directly in front of the mouth of the former English Channel River, because at that time, as I mentioned at the beginning, it was possible to walk between England and France. During the last glacial maximum, this area, the Manche or the Channel, was occupied by a massive river that was draining waters that were coming out from the British ice sheet melting and also from the different rivers that we know today, the Somme, the Seine, the Thames, the Rhine, and so forth. So we studied that core that was collected directly in the Bay of Biscay. So in order to study that core, we use a battery. I don't want to enter into any detail. We use a battery of different geochemistry tools, either molecular, isotopic, or inorganic geochemistry. This is just an illustration of the lab in Aix-en-Provence showing the molecular geochemical tools that we are using. We are using LCMS, we are using GCMS for different type of compounds. For example, we have been looking at the BIT index, the relatively new index that was proposed by the Texel team. the NIOS team, which is based on the ratio of different molecules that are synthesized by either bacteria or archaeobacteria, and these lipids are called tetraethers. And by using a ratio, a normalized ratio, it's possible, in fact, to be free of the dilution and to have a ratio that can be expressed independently of the sedimentation rate. So we call that the BIT index, or it was called, and we use that for our work. This is just a summary graph showing what was obtained, in fact, on that core that we studied directly in the output from the river channel. And I don't have time, in fact, to show you all the details, but the main part of the graph showing, in fact, the main input from the river Manche during the glacial is shown here in red. You have the BIT index, and what was a surprise, in fact, for us is that we could, with that proxy, it was possible, in fact, to identify a very early reactivation of the river during the last glaciation. As early as 21K, that there is already a pulse of heterogeneous organic matter at that time period, and it lasted several millennia with different pulses, but it is quite an early reactivation of the Manche or the Channel River. So this is something that was interesting, and we are trying to apply that to other cores, as I will show you. Obviously, during the glacial, the drainage of the Fennoscandian ice sheet was not only flowing through the west, it was also flowing directly to the south, and in that case, the situation is a bit more complex, because the melting was going first to Progrglacial Lake and then to a complex system of rivers, such as the Danube, the Dnieper, and so forth, that were all draining into not a Progrglacial Lake, but a lake, the Black Sea Lake. And at that time, because of the sea level drop, the Black Sea was a lake. It was disconnected from the Mediterranean. And we collected today several cores, especially one core that we are studying for that purpose, which is directly located in front of the Danube and the Dnieper. In addition to the organic geochemistry tools that I was mentioning at the beginning, we are also using high-resolution semi-quantitative tools that are based on micro XRF scanning and imaging. I don't want to enter into the details again, but this is something that is coming from the geochemical world that truly changed, in fact, the view paleoceanographers are doing paleoceanography today. More than, something like 10 years ago, this kind of tool did not exist, in fact, for us, and this really has changed life. This is the equipment, for example, that we are using in Aix-en-Provence that was installed. We, as a pilot study, we also study the sediment with another smaller scale micro XRF machine, and these are a few pictures showing that you can see at very high resolution. You can do even imaging of elemental imaging of calcium, strontium, iron, sulfur, and you can even see, here it's difficult to see that probably in the back and because of the quality of the picture, but on the original you can see individual grains, you can see individual forams. For example, here you have a forams that is void of strontium and is full of calcium. You can distinguish between the different phases of iron by using the iron and the sulfur. You can distinguish the sulfides from the oxide and so forth. So it's really a great tool that has really changed the life of paleoceanographer over the last few years. And we are also adding to this kind of tool, we are adding isotopic composition of certain elements that can be used, in fact, to fingerprint the source of the sediment. This is a map, in fact, that was compiled by Guillaume Soulet, a student in our group, former student in our group, that is showing, in fact, the simplified way, in fact, the different isotopic composition of neodymium expressed in epsilon neodymium coming out from the different tributaries. And of course, we should, by looking at this proxy in the core, we should be able, in fact, to see if there are large changes of the output. So this is the answer. I don't have the time to describe that fully in detail. If you are interested, you should see, in fact, the talk by Guillaume Soulet this afternoon at 3:30 in one of the sessions, 12E. Basically, the graph is showing what is happening in the early part of the last glaciation, between 10,000 and 25,000. And what we can see here is that there are massive impulse of flux from the rivers. As pulsed input, we get 4 layers of input of all those proxies. And the good thing, this is a good thing in paleoceanography when you see that 4 completely independent proxies are in agreement with each other in terms of the qualitative and also the quantitative changes. We can see that we can identify, in fact, the 4 layers of output from the rivers between 18 and 15K before present, based on the BIT index. We can study that also with the weathering of peat and soils with different compounds. I mean, here it's a graph showing the C25 N-alkane, but we have other compounds that are shown in a poster this afternoon. We have also the titanium over calcium ratio as a proxy for the terrigenous versus marine input that is based on the XRF kind of measurement that we are doing. And at lower resolution, we can use also the epsilon neodymium, in fact, to fingerprint and to identify very large changes of the output from the river. And this is a zoom, in fact, of this part of the last glaciation. What you can see, I mean, here in that blow-up between 15 and 17,000 years before present is that the system was functioning in a very abrupt way. And we don't understand it fully, but clearly all the markers that we use are responding in a very abrupt way. I mean, it's possible to even go down to the annual resolution with the XRF and to calculate the duration of all of these events. And the duration is on the order of a couple of hundreds of years, and this lasted on the order of more than a millennium. So everything, I don't want to, because I don't have the time, and it will be the role of Guillaume Soulet this afternoon, to describe what is our thinking about the functioning of the system, but everything is happening as if the complex system of the ice sheet, the progradial lake, and the system of river is functioning as a Japanese fountain. You know, it's being filled, and then it's releasing its load, and then it stays quiet in a glacial mode during some time period, and then it goes back, because overall, you have the melting of the ice sheet due to insolation. At the beginning of the talk, I mentioned the fact that most of the output from erosion and chemical weathering is coming out from the area that are affected by the Asian monsoon. So we are trying, in fact, also to study a few cores from that area. So this is just one example that is coming from the Gulf of Papua New Guinea. This is an interesting area, especially because during the glacial period, during the last glacial period, it was seriously affected. The monsoon was affected, but also the topography of the continent was affected because of the sea level drop. These are pictures that are showing, in fact, the topography during the LGM, and this is midway during the last glaciation. And basically, it was possible to walk between New Guinea and Australia on the Saul Shelf, and also on the west, you had also another shelf, the Sunda Shelf, that was above sea level. So we studied a core that is in the vicinity of the mouth of the Fly River. This river, I was not knowing it when I started, in fact, the work, but this is actually the largest, I mean, the first river in Papua New Guinea in terms of flux of sediment input, at least according to Milliman and Farnsworth, and it's number 13 globally today. And what we want to know is the past variability of the flux of sediment through time at that location. So we are using the different tools that I mentioned, organic geochemistry, isotopic geochemistry, and XRF. These are only graphs showing basically the data over the transition in plots of elements versus elements, just to show that the fluvial terrigenous output is dominated by aluminosilicate, so we could play with any of those elements, aluminium, silicon, titanium, or iron. One of the pitfalls of non-destructive XRF is that it is very sensitive to the water content of the sediment, and also you need a foil, in fact, to cover the sediment. So, in fact, it's not very precise for light elements like aluminium. So this explains, in fact, the scatter. So when we study and when we use those elements in proxies, when you do ratios, we prefer, in fact, to use elements such as iron, titanium, or calcium to compare with. So this is the results that we obtained so far, and for the moment it's really a preliminary work. This is, again, you have to imagine that we have a bench of, I mean, a lot of carbon-14 ages that allow us to build a chronology. On that graph, you have organic compounds such as alkanes, but also the BIT index that is varying through time by a large amount. And on the top of the graph, you have iron, titanium over calcium. I could have shown, in fact, many of other elements. They would still give the same answer. So when we look at the details, we can see that the whole thing is dominated by spikes. We don't see a tenfold increase of the load of the sediment output as in the graph that was proposed by, or shown in the paper by Vance et al. But we see instead millennial scale events or centennial scale events superimposed on the large changes that are mainly due to the increasing distance from the coast. But those events, in fact, when you look in details, they do correspond, in fact, to known climatic events. For example, the ones that are occurring over the last deglaciation, they correspond, in fact, to the Younger Dryas. They correspond to the Henrik event 1. And we can even identify H2 and H3, and they do correspond, in fact, we need, in fact, to increase the resolution of what we have done for organic geochemistry, but they do correspond also to increases of the BIT index. This one also corresponds to H3. So clearly, during the last deglaciation, we see an increase at that location of the output of the river. And everything, I mean, for the moment, the thinking about it is very preliminary, but very probably, given the knowledge that we have on the zone, the response is directly due to rainfall changes that are linked, in fact, to the ITCZ move during those time periods north and south. And very probably, in fact, this explains, in fact, the increase of the monsoon rainfall at that location that is giving a lot of detrital material. So I hope I was not too long again. In this talk, my intention was not, in fact, to make a broad review or to show and to describe in details what we are doing on the different fronts, but it was merely an illustration of how geochemistry really revolutionized paleoceanography in a way. Today, we can use geochemical proxies, both, with all three kinds: organic geochemistry, inorganic geochemistry, elemental geochemistry, and isotopic geochemistry of various elements to reconstruct the fluvial discharge over the last deglaciation. And basically, the long-time goal, one of my long-time goals, but it's also a long-time goal, a long-time objective for the whole community, is to produce maps, such as the map that was just released and updated by John Milliman and his colleague, for not only for the present day, but for the last glacial maximum, but also for the last transition, for the last deglaciation. So this is quite crucial that the community at large is trying to compare their results on the same rivers and at the same time to cover the world, not only for the present day, but also for the glacial maximum. And if you are not tired by this topic, I would like to recommend you a few posters and presentations today. I already mentioned the one this afternoon by Guillaume Soulet about the epsilon neodymium and biomarkers in the Black Sea. There is also a poster specifically about the biomarkers in the Black Sea output during the last glaciation. We have other two talks on using the tetraethers for paleoclimatology by Liz Sankey et al., Guillemette Meno et al., and another poster this afternoon about the Gulf of Papua core, mainly focusing on the comparison between micro-charcoal changes output and heterogeneous input to the area. So I thank you for your attention and for your patience.
Thank you, Edouard. We have time for a couple of questions. There are microphones in the alleys. Okay, so we will close this lecture. Thank you, Edouard, again for this very nice lecture. C'est bon? Oui, c'est bon. On avance, on n'est pas encore.